Hey everybody! You should have with you the worksheet entitled Newton's Law of Gravity. It looks like this. The goal for today is to finish the second page, therefore concluding the entire lab. Okay, your first task is to read those first two paragraphs. The first paragraph starts with, Newton's law has since been superseded by Einstein's theory of general relativity. Read that paragraph, read the next paragraph, and answer questions 1 and 2. Go! All right, so the answers to 1 and 2 on that page, you should have answered something like this. The inverse square law is written as, and of course you should have put in F equals 1 divided by d squared. And then it says where F is the force and d is the distance between the two objects. All right? And number 2, if the distance between two masses were to become large, then the force between them would become... Well, as a result of what we did on Friday, you should have known that as two masses separate, the force of gravity becomes smaller. So you should have written small. All right. The next thing we're going to do is number 3, using the inverse square law, complete the table below. All right, here we go. Okay, so what you see up on the TV screen there is the inverse square law. The image is just simply saying that the star is the blue blob on the top left, and as you progressively get further and further away, the gravitational pull between them is getting diluted. That is, it's getting spread out over a larger area, and therefore it's becoming weaker. Okay, so now we're looking at number 3, and it says, using the inverse square law, complete the table below. All you're doing is you're taking F equals 1 divided by d squared, and you're just putting in different d's. So F equals 1 divided by 1 squared. Well, what's that going to be? F equals 1 divided by 2 squared. Well, what's that going to be? F equals 1 divided by 3 squared. Well, what's that going to be? And F equals 1 divided by 4 squared. What's that going to be? Okay, crunch those numbers, and then we'll go over them together. Okay, so here we go. Let's go over the answers. So 1, if we use the equation, the inverse square law, which says, where is it at? There it is. F, the force equals 1 divided by d squared, the distance squared. So if we put 1 in for d, that's really just 1 divided by 1 squared, which of course is 1 divided by 1, which of course is 1. And I am taking it out to 4 decimal points for a reason you'll see in just a moment. Okay. So if we do the same thing again, but use the distance 2, it's going to be 1 divided by 2 squared. Well, 1 divided by 2 squared is 1 divided by 4, and 1 divided by 4 is 1/4, which translates into 0.2500. Did you get that? Doing it again, let's continue. Let's use 3 for d. 1 divided by 3 squared is the same thing as 1 divided by 3 times 3, which is 9. 1 divided by 9 is 1/9. And if you do that on the calculator, it turns into 0.11111111 forever, which I will abbreviate or round to 0.1111. All right, almost done. 1 divided by d squared. Well, let's put in 4 for d. 1 divided by 4 squared. Well, what's 4 squared? I believe 4 times 4 is 16. So 1 divided by 16 is 1/16. And you crunch that number and you get 0.0625. Okay, cool. We now have a data set that we can graph. Okay, so we're taking those 4 numbers of the force of gravity that we just calculated, and now we're going to plot them on the graph that's right below it. So as it says in number 4, plot the data in the table above onto the graph below. Notice on the x-axis we have distance, d, which is that number there. And notice on the y-axis we have the force of gravity, which is, of course, those numbers there. All right, plot those and I'll go over the answers. Okay, so this is what I got. Hopefully you got the exact same thing. Notice when we plot them, we get the first number way up here, and then the next number way down here, the next number way down here, and the next number way down here, and I, of course, connected them with a line, making this a line graph. All right, that's what it looks like, but now the question is, the goal is to interpret that graph. So the next item is to describe what happens to the force of gravity as you get further away from a star using that data, or I should say that data that you just plotted. Hopefully this is simple and you already know it, but write it down in a complete sentence. All right, this is what I wrote. Let's see what you got. I got that the force of gravity between a star and a planet decreases rapidly as distance between them increases. You should have gotten something very similar to that. All right, get that and we'll move on. Okay, we are now moving on to the very, very last page. It looks like that. And you are to read the first two paragraphs and try and understand that graph that's right there. Okay, bye. Okay, the main thing that you should have gotten from this is that Newton's law can be simplified to just simply F equals ma, as it shows right there. And that simply means force equals mass multiplied by acceleration. Okay, the next part is not really difficult, but in comparison to everything else we've done, it becomes slightly more difficult. It really just means that you pay attention to what you're reading. So read the paragraph right there at number 5. Okay, so what I read at number 5 is this. Using Newton's law of gravity, which is force equals g multiplied by m1 multiplied by m2 divided by r squared, and his second law of motion, F equals ma, calculate the acceleration of the planet above at points A, B, and C, using the given information below. In order for you to solve for acceleration, you need to algebraically rearrange F equals ma. So write this modified equation there. So do it. If you want to solve for A, what do you got to do to make it work? Ready? Figure it out. Go. Okay, this is what I got. If I want to solve for A, then you simply take the m and divide by that on both sides, and it cancels out on the A side, therefore eliminating it, and then it needs to appear on the F side. So therefore you see what I have here, A equals, acceleration equals force divided by mass. Make sure you write that down. Okay, and the next step is to fill in that table, A, B, C, and it also says acceleration. So this is the part that's not totally difficult, but a little bit more difficult. You need to first solve Newton's law of gravity, which is F equals g multiplied by m1, m2 divided by r squared. You need to figure out what the force is. So you need to plug in these numbers to calculate the F, then you take the number you got for F and you plug it into A equals F divided by M. And then you also use the M that we have down here to figure out acceleration. And you put that number here in A. Then do the same thing for B, and then do the same thing for C. A being the planet A right there, and B being the planet B, and C being the planet C there. And notice in the data that's given in the box that there is RA equals 1, RB equals 4, RC equals 5. So you're using those R's in the Newton's law of gravity over here. So really, you're doing this 3 different times, A, B, and C. The only difference is that you're putting a different R each time. Good. Okay, so what are the answers and how did I get the answers? All right, here we go. So there's the table, acceleration. We want to find the acceleration for planet A, which is there. It's a small distance from the star, the sun. There's planet B, which is a greater distance. And then C, which is even a greater distance. Okay, so here's what I did. You can see here I have planet A, planet B, planet C. And here's what I did mathematically. I wrote in the equation F equals G multiplied by M1 multiplied by M2 divided by R squared. And so if we throw in the numbers that we see in the box, what we get is G is 0.001 multiplied by M1, which is 10,000, multiplied by M2, which is 10, divided by 1 squared. Remember that 1 is coming from here where it says R of A, the radius of A is 1, which is that distance from there to there. We're just calling that 1. So anyway, we put that 1 in there squared. Well, the top part equals 100, the bottom part equals 1, because 1 multiplied by 1 is 1. So 100 divided by 1 is 100. Therefore, F equals 100. We're not done though, because we take that 100 and then we come and we know that we need to figure out A. A is the acceleration that we want to figure out. There's acceleration. We want to figure out acceleration. A is acceleration. So what we do is we rearrange this and we get this, which is A equals F divided by M. And if we plot in that 100 from over here to F, we get 100 divided by 10, which is the mass of the planet. 100 divided by 10 equals 10. So therefore 10 equals A. And so we come over here to A and we put 10. Okay, let's do the same thing for planet B. And again, planet B is right there, and we got to figure out that distance and the force that it has, and then eventually the acceleration. So here we go with B. So again, we come over here. There's planet B. I come down. Once again, there's F equals G multiplied by M1, M2 divided by R squared. Well, we know the top part, G, M1, M2 equals 100. We know that from the previous exercise. None of those numbers have changed, and we know it equals 100. So I'm just going to immediately say it equals 100. But what has changed is the R. R, in this case, is 4. Remember where we got that? We got that from right here. R of B equals 4. And again, B is this planet here, and the R is the distance between B and the sun. So that radius is 4. I put that 4 here. 100 divided by 4 squared is the same thing as 100 divided by 16. If you do that mathematics, then you get 6.25. But we're not done, because 6.25 is the force. But what we want is the acceleration. So again, we have rearranged F equals ma and changed it to A equals F divided by m, and we plug in these numbers. So F, as we got over here, is 6.25, so therefore it is 6.25 there, and the mass of the planet is still 10, and if you do that division, you get 0.625 equals A. So A equals 0.625. So we take that number, we come over here, and there is B, the planet B, which has an acceleration, which is A, of 6.25. Alrighty, last one, planet C. So here we go. There's planet C. It's got that great distance to the sun. That's called R. We're using R of C, which is 5. And we're coming over here once again to F equals G multiplied by M1, M2 divided by R squared. Well, again, that top is worth 100. We found that out in the first planet A. So there it is, 100. And the R squared is now going to become 5 squared. And of course, 5 squared is 25. So 100 divided by 25. And there it is, 100 divided by 25. And when you do that calculation, it turns out to be 4. So F equals 4. Cool. And we're not done, of course. We come to that equation, A equals F divided by M. We're after A. A is what we want, but we know F and we know M, so we can plug those numbers in. So we took the 4 from F that we just calculated. So 4 divided by the mass of the planet, 4 divided by 10 equals 0.400, which equals the A, which is acceleration, which is what we were after. So we come back over here to the table and we put in that number 0.400, and that is the acceleration of planet C as it's going around that star called the sun. Okay, now we need to do questions 6, 7, and 8. Hopefully you can figure them out. Here we go. Okay, so we are looking at numbers 6, 7, and 8. Let's start with number 6. What 6 says is, what happens to a planet's acceleration as it gets closer to a star? Well, let's figure that out. So here's that diagram. There's C, which is really far away from the star. There's B, which is a little closer. And there's A. And so the question is what happens to a planet's acceleration as it gets closer to a star? Well, planet A is really close, and if you look at the table of numbers, A is 10, B is 0.65, which is really small, and C is 0.400, which is even smaller. So it looks like the acceleration increases as you get closer to a star. The acceleration increases as you get closer to a star. Okay, so let's look at number 7. 7 is asking a very similar question, but the opposite. What happens to a planet's acceleration as it gets further from a star? Well, guess which one represents that? Is it A, is it B, or is it C? Well, C, because it's the furthest from the star in this diagram. And as we can tell down here, it has the smallest number. Therefore, a planet's acceleration is at its lowest as it gets furthest from the star. Okay, now we're looking at question number 8. It says, remembering Kepler's second law, at which of these orbital locations, A, B, and C, does the planet have the greatest velocity? Velocity, acceleration, velocity. So let's think about that. Acceleration is you speeding up. Velocity is just how fast you're going. So really, acceleration is a change of velocity over time. So the question is, where is the acceleration the greatest? Where is the velocity greatest? Those are two different things. The question says, remembering Kepler's second law, at which of these orbital locations above does the planet have the greatest velocity? Well, if you remember, that greatest velocity was A. That's where it's going its fastest. And then it asks orbital location of lowest velocity. That would be C. So notice that the acceleration is at its lowest in the same place where its velocity is the lowest. The acceleration is at its greatest in the same place where its velocity is the greatest. I hope that helps. I think you were now able to finish this lab.